Doing pretty well. Once we wait just another minute or so, we'll get started back up. We have to pick back up from around the middle of 2.2. We're going to finish discussing 2.2, and we're going to begin discussing 2.3 today. Is this really all that's going to attend today? Today's our normal lecture. Huh. Well, all right, let me grab my tablet here. I'm a little bit hungry as I have these kind bars that are peanut butter filled that typically only I eat because my wife doesn't like peanut butter, but inexplicably she ate the last one out of nowhere. I was shocked. All right, let's talk about some math. Only 6 people. Only 6 people. Wow. Did I scare everyone off? Huh. Today's a normal lecture, right? Today's one of our scheduled lectures. Unusual. All right, let me just start a new page here. And let me begin recording. So last time, the last thing that we did was we evaluated the limit of sine of x over x as x approaches 0. We determined that that is equal to 1. We determined that by looking at the graph of the function. It appears that as our x values get close to 0 on that function, that our y values appear to get pretty close to 1. Today we're going to continue our discussion of limits, but we're going to discuss this idea of one-sided limits, beginning by discussing what's called the Heaviside function. The Heaviside function sometimes denoted h, I suppose. This is defined as, put a comma there. This is defined as h of t is equal to 0 if t is less than 0, or 1 if t is greater than or equal to 0. This is a pretty simple function, right? We might be able to imagine what this looks like if we were to graph this. This is just going to be 2 horizontal lines. Do we agree? If a horizontal line at y equals 0 with a hole, and then at y equals 1, you have this closed circle because we are defining that function value. And it looks like this, right? Does that make sense? That this is what the graph of this would look like? Yay, nay. Do I teach Calc 2? I'm not in the fall. I'm not teaching Calc 2 in the fall. This is still 2.2. You understand the function, but not how it plots on the graph. So this is a piecewise defined function, it's saying that my y values are 0 if t is less than 0, and my y values are 1 if t is greater than or equal to 0. There's a jump here between these y values. We don't understand how. Right, this is y equals 0 if these here. This is supposed to represent an electrical current that is switched on at time t equals 0. Yeah. Yeah, the bottom one here has an open circle, exactly, because this first interval where t is less than 0 does not include 0. This top portion of the graph has a closed circle because the second interval is defined for t is greater than or equal to 0. The big idea with looking at the Heaviside function being that what if I try to find the limit as t approaches 0 for the Heaviside function? I can't do it, right? Do you agree that there's no single value that my function here is approaching as my t values are getting close to 0? It's not so much undefined as it is that this does not exist. We would say that this limit does not exist. We'll often abbreviate this D and E. Now I can define limits for this function if I look at this function by approaching 0 from either side. If I approach t equals 0 from either side of this function, I can define separate what we call one-sided limits. I could define, for instance, the limit as t approaches 0 from the left of h of t with this superscript minus sign. This represents t approaches 0 from the left. What's going to be the limit of this function as t approaches 0 from the left? Zero, right? And approaching 0 from the left, we mean approaching 0 from values that are less than 0, right? So getting close to t equals 0 from the left, we get this y value of 0. Now, what's the limit as t approaches 0 from the right of h of t? This would be 1 instead, right? So if I approach t equals 0 from values that are greater than 0, then I'm looking at this branch of this piecewise function. And as my t values get really close to 0, my y values are getting close to 1. Does this make sense? So notice that something can have one-sided limits that are not equal to each other, right? These two one-sided limits are not equal to each other because of the way in which this function is defined. So let's get a little text box with a generic definition of one-sided limits. How about it? Beep and boop. There we go. We write limit as x approaches a from the left of f of x, or the limit as of f of x as x approaches a from the left, equals L, and say that the left-hand limit of f of x as x approaches a is equal to L if we can make the values of f of x arbitrarily close to L by restricting x to be sufficiently close to a with x less than a. Same idea with a right-hand limit. We say, or we write this, right? And we say that the right-hand limit of f of x as x approaches a, or the limit of f of x as x approaches a from the right, is equal to L if we can make the values of f of x arbitrarily close to L by restricting x to be sufficiently close to a with x greater than a. Do these definitions of left-hand limit and right-hand limit make sense? It does now. And everyone's so boring with saying yes. Everyone's only saying yes in English or Spanish or French. I never see any languages. I never see any yeses in English or Spanish or French. that's a language. That's for sure. Today was so blah. I mean, I expect for everyone to start learning yes in other languages. So let's look at some more examples here. Oh yeah. Here's an example of the contrast between these limits. Let's look at some graphs. In the left graph, we have a left-hand limit. On the right graph, we have a right-hand limit. Does this make sense? Do these graphs help us to visualize what's going on here as well? Yeah. No one else has a non-English alphabet on their keyboard. Is it just me? Now, there's an important definition that follows from our definitions of one-sided limits. These one-sided limits could be equal to each other, right? And often they are going to be equal to each other. Although I suppose our definition of often may vary, right? The limit of f of x as x approaches a equals L if and only if the limit of f of x as x approaches a from the left is equal to L, and the limit of f of x as x approaches a from the right is equal to L. So in order for a limit of a function to exist, our one-sided limits have to both equal that value. Our one-sided limits have to be equal to the same thing. And if our one-sided limits are the same, then we have a limit. Does that make sense? It does not. An example being with this heaviside function, our left hand and our right hand limits are not the same, right? Because these one-sided limits are not the same, we say that the limit does not exist. Because in order for the limit, just the limit as h of t as t approaches 0 to exist, these two limits have to be equal to each other. If we had a function where these two one-sided limits were the same, then the limit as t approaches 0, for instance, would exist in that case. Does that make sense? Cool. Yeah, no problem. Let's look at an example. How about it? Examples are nice. Yeah. Yes. We don't explicitly call them two-sided limits, but our standard definition of a limit kind of relies on these. Our standard definition of a limit that we looked at earlier relies on these one-sided limits to be equal to one another. Does that make sense? Cool. Because it's just a way of saying, before I even give us the problem here, for instance, on this function, this is x. This is called g of x. If I want to find the limit as x approaches 0 from the left, yeah, I can. How do I find, so what is the, of this function, what's the limit of g of x as x approaches 0 from the left? Looks like about, wait, what are these? 2, 3, looks like about 2.5. This one's tricky, right? Looks like it's between 2 and 3. 2 is just not labeled. What's the limit as g of x, or what is the limit of g of x as x approaches 0 from the right? So this time from the right. What's this equal to? It's also 2.5. So because these limits are in agreement, we say the limit as x approaches 0 of g of x, or really it's supposed to be the limit of g of x as x approaches 0, is 2.5. Does that make sense? Cool. Can I leave it up a bit? Yeah. Well, I need to scroll down just a little bit because, well, I need to zoom out a little bit, I suppose, because I need to copy the additional problems over here. Group. How would they not be the same? Well, like in the heaviside function that we looked at earlier. Or let's look at let's look at A and B right here. What's the limit of g of x as x approaches 2 from the left? It looks like it's 3 to me. What do we say? How? So as I approach, we're looking at both. As my x values are approaching 2 from the left, what's happening to my y values? As my x values are approaching 2 from the left, what are my y values getting close to? My y values are getting close to 3, right? Do you see that my y values are getting close to 3 as my x values are getting close to 2? This means that the limit of g of x as x approaches 2 from the left is 3. What's the limit of g of x as x approaches 2 from the right? So as my x values are getting close to 2 from the right, what's happening to my y values? What are they getting close to? They're getting close to 1. Brain offline. It happens. And now, these two one-sided limits are not equal to each other, are they? So what's the limit of g of x as x approaches 2, which is c? Does not exist. Yeah, we can write d and e or does not exist. Does this make sense so far? Yes, but what's the exception here? What doesn't make sense? Yes, from the left. Yes, from the right. Yeah. The minus sign means we are looking at values that are less than 2. The plus sign means that we are looking at values that are greater than 2. Does that make sense? One-sided limits is definitely 2.2 in the textbook. As long as we're looking at the same edition. The precise definition of a limit is 2.4, which we are not going to talk about. It's not always 2. It's just in this example. We were just looking at approaching this x value of 2. Because we have these examples D, E, and F, for instance, where we're looking at x approaching 5. So let me erase these, and let's look at D. The limit of g of x as x approaches 5 from the left. What is this? Maybe I'll make this a little larger. What's the limit of g of x as x approaches 5 from the left? Each of these things is 1. Yeah, each of these things is 1. So yeah, that makes this 2. So the limit of g of x as x approaches 5 from the left is 2. What's the limit of g of x as x approaches 5 from the right. It's coming in this way. Also 2. What's the limit of g of x as x approaches 5? If my two one-sided limits are equal to each other, then my limit is the value that those two one-sided limits are equal to. What is g of 5? G of 5 is 1. The point of this is to say that the limit of a function as that function approaches a certain value is not necessarily the same as its function value at that x value. Because g of 5 is not the same in this case as the limit of g of x as x approaches 5, is it? Yes, it's because of the dot. It's because there's a hole at g of 5 in this curve. The shaded blue circle, this means that they have defined that x value to be g of 5 equals 1. Or they've defined this function here. Because there's a hole at g of 5 normally without that dot. Right, the open circle means that that point is not included on the graph. Right. The intended answer here is definitely 1. I think if I busted out my iPhone here and did a little bit of look, because I'm a pro, I have the Pro Max. I think I could think if I were to use my level function here, that we would find that this is level. Yeah, I'm a pro, so I got the iPhone Pro, the 12 Pro Max. I think it's level. So let's move on. I haven't had a flagship phone in quite some time, so I was like, I deserve it. What would this look like when graphed? What do you mean? This is the function graphed. So it would look like this. Let's see. So let's investigate how a limit can fail to exist. Let's investigate this one. Oh, that's small. There we go. What equation would make this graph? I don't know. We could come up with some kind of like maybe a logarithmic curve here, and this would be a piecewise defined function. It doesn't matter too much. Let's investigate the limit of sine of pi over x divided by rather let's investigate the limit of sine of pi over x as x approaches 0. Okay. Well, this is definitely undefined at 0, right? We can definitely make a note of that. This is undefined at 0. Because I can't divide by 0, right? Even inside of this trigonometric function, I can't divide by 0. How do you think that we should go about trying to find the limit of this thing? Graphing is one viable strategy. Multiply by pi. So TI-84 is probably not going to do too great of a job at graphing this, to be honest. It's going to get a little bit messy on the graph. But perhaps what we might do is try plugging in some really small values before we go to a graph, right? Let's try plugging in some really small values of x, or some stuff that's pretty close to 0. Let's start out with f of 1. F of 1 just becomes sine of pi, right? What's sine of pi? What's sine of pi? Oh, my 172 students. My 172 students better be telling me what sine of pi is. It's 0. So let's find f of, let's skip a few here. Let's go to f of 1/4. What do I get if I plug 1/4 in here? Well, I get, ends up I get sine of 4 pi. What's sine of 4 pi? This is also 0. There was no warning. What's f of 0.1? Huh. This ends up being sine of 10 pi. That's 0. What about f of 0.01? This is sine of 100 pi, which is, yeah, this one's 0. Sine of n pi is 0, right? Sine of any integer multiple of pi is always 0. Always, always. Always, 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 always. Because those are the far left and far right portions of the unit circle, right? So, on the basis of this, what do we want to guess that the limit is then? We want to guess that this limit is equal to 0. Ends up this is wrong. This is super wrong. No, it's not, because so something can be undefined at the place that we're approaching and still have a limit there. For instance, here on this graph, right? This has a limit as x approaches 5. Even if we didn't have this point here, this would still have a limit as x approaches 5, right? That limit is equal to 2 in this case. Now, the reason why we're wrong is there are all of these numbers that we plugged in that would have yielded a different answer, right? We could have plugged in answers that would have given us something different. For instance, what if I plugged in f of, let's see here. What if I found f of 2/3? This would have been sine of 3 pi over 2. What's sine of 3 pi over 2? This is at the bottom of the unit circle. This is -1, right? Similarly, there are values that we could have plugged in here to get +1. In fact, if we look at a graph of this thing, has anyone tried to graph this? You did? Oh, it's crazy. Yeah, let's look at it. I hope that your heartbeat doesn't look like this. If your heartbeat looks like this, you need to go to the hospital. Like, so this, what do you think is happening here? What do you think is happening as we get close to 0? Why do you think we're just wrong about this limit? What's happening as this function's getting close to 0? This function is oscillating between 1 and -1 infinitely often as x approaches 0. Right? So what's happening is the function values do not approach a fixed number as x approaches 0. The function values here do not approach a fixed number. That was English. That was plain English. The only word I use that's an out there word that you have heard before is oscillate. So the reason why this, why we're wrong here is, again, the values of this function oscillate between 1 and -1 infinitely often as x approaches 0. So the values of this function do not approach a single number as x approaches 0. As a result, this limit does not exist. Does this make sense? Does it make sense why this limit doesn't exist, at least? Yeah, I can scroll up a little. Let's investigate another case here. What about if my, wait, you don't know? You don't know about what? Why it doesn't exist? Let me pull that graph back up. Let me take a screenshot. This function is not approaching a single value as x gets close to 0. The function is oscillating so rapidly that it does not approach a single value. And because this function does not approach a single value, as x gets close to 0, the limit as x approaches 0 does not exist. Because for the limit to exist, the function has to begin to approach a certain value. Can you determine that without a graph? Yeah, we could determine it analytically. If we continued to plug in sufficiently small numbers here. Just simply avoiding ones that lead us to 0. We'd be able to see this function continues to oscillate. For instance, by plugging in 2/3, we get -1 out of this, right? Similarly, f of x, the function values are equal to 1 if you plug in something like 2 over 101. This ends up giving us +1. Things like that. Now let's look at another way that a limit can fail to exist. How did I plug in into Desmos? I just typed sine of pi over x. This is what it looked like. Like this. The limit does not exist. The limit as x approaches 0 of sine of pi over x does not exist. Yeah. Has anyone seen Mean Girls? Isn't the limit does not exist a line from that movie? I was pretty sure that someone says that in that movie. We watched Mean Girls in my AP calculus class in whenever I was a senior in high school. Let's look at this limit. This is going to be pretty easy to tell what's going on. For the sake of brevity, we're just going to skip straight to looking at the graph because in my brain, I can picture what this looks like because I've seen this enough. Some of us may have also seen this enough to know what the graph is going to look like. What's happening to my function values as x gets really close to 0? What's happening to my function values here? They never touch, but what are they getting close to? Or what are they trying to approach? What are they getting close to, quote unquote? They are increasing forever, right? My function values for this graph, as x gets close to 0, these function values are going up forever. Do we agree? Because there's a vertical asymptote here, right? So we say that these, we could say that these function values grow without bound, for instance. Or we could say something like the limit of 1 over x squared as x approaches 0 equals infinity. This is kind of, I'm not a fan of this. To me, this limit does not exist, right? However, sometimes notationally it can be convenient to represent it in this way, right? If you were to say that the limit does not exist here, you would not be wrong. This limit doesn't exist. We're just saying that this is a way of expressing the way in which the limit does not exist. We're using the limit to express the way in which the limit does not exist. Does that make sense? We're saying that the limit does not exist because these y values No, so we're essentially saying that the limit does not exist here because there's a vertical asymptote that's causing my y values to increase without bound. Or just simply that my y values increase without bound as my x values get close to 0. We're also not treating infinity like a number here. All we're saying here is, maybe this is a better way. 1 over x squared can be made as large as we like. By taking x close to 0. Or close enough to 0. Does that make sense? That's kind of what writing this as a limit represents. Or we could say 1 over x squared increases without bound. As x approaches 0. Does this make sense? Yeah, so this is just describing the way in which a limit does not exist. This limit technically does not exist, right? Because the idea of a limit is I get, as my x values get really, really close to something, then I can make my y values get really, really close to a certain number, right? How would you get the graph of 1 over x squared? You just type, you go to Desmos, you type boom, 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 boom. This should get you the graph. Just using the caret symbol here. So let's get a little box with that info in it. This is an intuitive definition of an infinite limit. Oh yeah, some calculus deals with infinity, so get used to it. Let me go ahead and grab the complement to this. These things say the same thing. I'm pretty sure, let's see. These are literally exactly the same words, but exchanging things like arbitrarily large with the phrase arbitrarily large negative, and exchanging really that's it, right? The infinity for negative infinity. The idea is that this can happen with function values going down as well, right? If both branches of my graph can go up, it's a possibility that I can have a function where both branches go down, like in this case. Does that make sense? So that's nothing. That's nothing groundbreaking per se, right? This definition 5 here is the same as definition 4. It's just saying that if a function can look like this, then we could have something that resize, move. We could also have something that looks like this, essentially is what it's saying. And in this case, this would essentially be the graph of negative 1 over x squared, and the limit as x approaches 0 for this is going to be negative infinity, is what it's saying. Does that make sense? No problem. And we have, oh yeah, this also applies to one-sided limits. We can have one-sided limits that are infinite as well. Although I feel like that kind of, that perhaps goes without saying. Does it? Do you feel as if it goes without saying that this applies to one-sided limits as well? Yes, okay. Yes, you can have positive or negative infinity here. Your infinite limits can be positive infinite or negative infinite. No, so no. It's saying if you have a graph of a function like this, for instance, as x approaches a, the limit as x approaches a of this function is negative infinity, because both of the branches of this graph are decreasing without bound. As this graph gets sufficiently close to a, these y values are spiking downwards. Does that make sense? Okay. This is a definition that we have seen in the past, but now we're just using limits as well. Oh, I was just giving that as an example. I was just flipping the graph around because that was an example of a positive infinite limit, and I just wanted something that was a negative infinite limit. Yeah. The vertical line x equals a is called a vertical asymptote of the curve y equals f of x if at least one of the following statements is true. The limit of f of x equals infinity as x approaches a. The limit of f of x equals negative infinity as x approaches a. Or any of the variants of that involving one-sided limits as you see before you now. This is just redefining the idea of a vertical asymptote in terms of the language of calculus. For instance, let's look at this example. Does the curve y equals 2x divided by x minus 3 have a vertical asymptote? Yes. Yes, this does have a... Oh, you shouldn't have to graph this. This thing does have a vertical asymptote. As a vertical asymptote at x equals 3. If we were to graph it, we would obtain something that looks like this. The graph doesn't graph the... or did I say horizontal? I meant vertical. The graph doesn't graph the vertical asymptote for you because that's not a feature. Like it's not a line that is graphed with the function. So what's the ones? Let's look at the one-sided limits of this function as x approaches 3. Sorry, I get a little excited and I forget how to talk. How can you know that this has a vertical asymptote? Because there's going to be somewhere in this denominator. There's going to be somewhere in this denominator that is equal to 0. Anywhere where my denominator is equal to 0 can cause a discontinuity in my graph. And if I cannot remove that discontinuity through some factoring and cancellation, then it is a non-removable discontinuity, also known as a vertical asymptote. How do I know where a horizontal asymptote would be? You have to compare the degree of the numerator to the degree of the denominator. In this case, there is a horizontal asymptote at 2 because the degree of the numerator is equal to the degree of the denominator. The solution from the book, the solution to what? To this example? I was about to. So let's inspect the one-sided limits here. What's the limit of 2x over x minus 3 as x approaches 3 from the left? What's happening to my y values as x approaches 3 from the left? So what are they getting closer and closer to? So we're going to write negative infinity here, right? Because they're decreasing without bound. What's the limit of 2x over x minus 3 as x approaches 3 from the right? They're rocketing upwards, right? They're growing without bound. So we say that this is equal to positive infinity. Because these one-sided limits are not the same, we can't write this as either the limit as x approaches 3 of this function is equal to infinity, or the limit as x approaches 3 of this function is equal to negative infinity, because these one-sided limits would have to be the same for us to write that. Instead, we can just say the limit does not exist. We can just say the limit of 2x over x minus 3 as x approaches 3 does not exist. Does that make sense? We'll skip the part where we find all of the possible vertical asymptotes of the tangent function. That one's pretty simple. The tangent function has vertical asymptotes everywhere where cosine can possibly be equal to 0. So that's going to be at n pi over 2. Any multiple of n pi over 2, essentially. Or pi over 2 plus n pi is how they write it. Oh, that was copy-pasted. That was not organically typed. I can tell. That was not typed. You can't just type in another language? The last bit that I want for us to look at in 2.2 is the vertical asymptote of the natural logarithm. That's konnichiwa. Konnichiwa. Hello. The vertical asymptote of the natural logarithm is negative infinity. So this specifically only has a one-sided limit. This doesn't have a two-sided limit or a regular limit because, well, we can't approach x from the left with this logarithm, can we? And in my logarithmic function, the way, as my x values get closer and closer to 0 from the right, my y values go downwards towards negative infinity. So let's look at 2.3. 2.3. We are discussing laws, and I am the judge, jury, and executioner. Oh, let me get a better screenshot than that. We're discussing limit laws. These are properties of limits that allow us to calculate limits from other limits. So suppose that the limit of f of x as x approaches a and the limit of g of x as x approaches a exist. Sometimes in variations of these limit laws, they go ahead and they give names to these limits. For instance, like L and M or something like that. Sometimes they give names to these limits. So if you look at these limit laws on another resource, you might see that they like call this one L and maybe they call this one M or something like that. Maybe they're different letters, but sometimes they give these names. Then the limit of f of x plus g of x as x approaches a is the limit of f of x as x approaches a plus the limit of g of x as x approaches a. So number one is saying the limit of the sum is what? The limit of the sum is the sum of the limits. Very good. Number two is a difference law. The limit of the difference is what? The difference of the limits. Number three. I don't really have a fancy phraseology for this one. Just the limit of a constant multiple times a function is equal to that constant multiple times the limit of the function. We can maybe say limit of constant times function is constant times limit of function. We're just allowed to take that constant and move it to the outside of the limit is the idea here. This is a constant multiple law. Yeah. We have a product law. The limit of the products is the product of the limits. Nice and simple. It's not going to be this simple once we get to derivatives, by the way. So buckle up. And the last one here, the limit of the quotient is the quotient of the limits except if the limit of except if the denominator is 0, right? Or as long as the bottom limit is not 0. I write these out just because maybe having these in words will help some of us. I don't know if it does, but perhaps it will. Sometimes seeing it in words instead of just a bunch of math can be helpful. And some of that's fun to say. The limit of the sum is the sum of the limits. Nice. The textbook literally has all of this almost exactly as I typed it, and I wasn't reading. I wasn't reading off it. Oh, man. Dang, he's good. All right, do we have this? Can we move on? Let's look at an example. Missed last semester's class? Why? I like this class. Are you a calculus hater? I like this. I like this class. I like calculus. Calculus is fun. Oh, you don't even know what you're hating yet. We've barely scratched the surface of calculus. Let's use the limit laws and the graphs of f and g in figure 1 to evaluate the following limits if they exist. So f is the red function here and g is the blue function. So the limit of f of x plus 5 times g of x as x approaches -2. What I would probably go ahead and do in this case is I would find these limits individually. What's the limit as of f of x as x approaches -2? Looks like it's right here. Right. So that is 1. What's the limit of g of x as x approaches -2? It looks like -1. Yep. So this means that using our limit laws, this limit is equal to, this was 5 times, right? The limit of f of x as x approaches -2 plus 5. I suppose I should first write the limit as x approaches -2 of 5 times g of x. And now I use my constant multiple law to bring the 5 in front of that second limit. Well, the limit of f of x as x approaches -2 was 1 plus 5 times the limit of g of x as x approached -2 was -1. And this is going to be -4. Can I scroll up? Yeah. Does this make sense? Slowly making sense? Okay. Slowly but surely. Let's look at B. I have a limit of a product. So what I should do is I should find these limits individually, like I just did. The limit of f of x as x approaches 1. What is it? Do we agree it's 2? What's the limit of g of x as x approaches 1? Well, look at g of x. G of x has 2 separate one-sided limits, doesn't it? So what we have to do is we have to apply this limit law for the one-sided limits here. Although, let's see, this says that these limits have to exist, right? I don't think that we have to go so far as to say that we need to check out the one-sided limits here. I think that if one of these limits doesn't exist, it's safe enough for us to go ahead and say that their product does not exist. What do you say? This seems to mean that this limit does not exist. Yes.
So if there are two sides, and they meet at the same value on the x-axis, it always does not exist.
So if there are two branches here and they have two separate one-sided limits that are not equal to each other, then the limit at that x value does not exist.
Okay, and what if they were two open circles and they like met or something?
So if they were open circles, but they say met like right here, but they're both open circles, for instance, do you mean like that?
Sorry, my thing is like glitching. Yeah, like that.
Then the limit exists. It's okay if the function value does not exist. It's totally fine if the actual function value does exist, because the function value is not necessarily equal to the limit anyway, even if it does exist.
So there's Are you saying there's still a limit even though there's no value there?
Yes. Yeah. Because the idea of a limit isn't necessarily the idea of having a value there. It's the idea of being able to get arbitrarily close to a certain value.
So kind of like how we said the limit of f of x as x approaches 1 is 2, even though you didn't specify which side we were coming from, because it reaches like a maximum there, we can just call it a day and say it's 2.
So the reason why you can say that, because that portion of that graph is continuous. There's no jump here, right? So in this case, the function value is equal to the limit. Over here, though, for instance, as x approaches -2 of f of x, the actual limit is the value that the graph is getting close to as the graph gets really, really close to -2. So the limit of f of x as x approaches -2 is 1. But f of -2 is 2.
Okay, that makes sense. You may proceed.
Awesome. Let's see. And the last one here, the limit here, the limit as x approaches 2 of f of x divided by g of x. So it'll be helpful to find those limits separately. So the limit of f of x as x approaches 2 is, it's a decimal, right? It's maybe 1.4 or 1.5. We'll say 1.4. The limit of g of x as x approaches 2 is what? It does exist. It's just equal to 0. This is a common, and I'm glad that you said that, because this is a very common point of confusion. A limit being equal to 0 does not mean that the limit does not exist, right? This is a very, very, very common point of confusion in a calculus class. Very, very common. So, I'm glad that I saw that now and not later. A limit can exist and be equal to 0, right? Does that make sense? Many calculus students, many calculus students make that mistake. Very common, maybe the most common calculus mistake. So from my limit laws, this limit is equal to the quotient of the individual limits, right? But that would be 1.4 divided by 0. And remember, this explicitly says as long as the limit of g of x as x approaches a is not 0. So this means that this limit does not exist for c. Does that make sense? Yes. Excellent. Let's look at A few more laws. I am the law. Here's a few more. Not the first time you read it in the book, but it does now. Yeah, sometimes these math textbooks don't make much sense whenever you read them. There's something about the phrasing. It can be, I mean, even if I try to self-study a math topic, it can sometimes be a bit difficult, right? You really have to be paying full attention, and you have to make sure that you know, sitting there with pencil and paper taking notes and stuff. It's a very difficult process. It's very mind draining. We have a power law as well. We call it the power law because it's strong. That's a joke. The power law is just the limit of a function raised to a power is the limit of that function raised to that power. Maybe that one was phrased poorly. If I have a function raised to a power and I want to find the limit as x approaches a, I can find the limit of that function not raised to a power and raise that limit to that exponent instead. Does that make sense? It's no. For instance, if I had the limit as x approaches 1 of x minus 3 to the 10th, I could instead find the limit as x approaches 1 of x minus 3 and raise that answer to the 10th power. Does that make sense? So this one's the function being raised to a power, right? On the right-hand side, it's the numerical answer of the limit being raised to a power. Does that make sense? And it's often going to be easier for us to find the one on the right, right? It's often going to be easier for us to go ahead and find a limit and then raise that number to a power. A similar property that's derived from the power law here is the root law. So finding an arbitrary root, or rather finding the limit of a function of which the which is, how do I phrase this? Sorry, I'm just trying to think of how to rephrase this in plain language. If I have some function in the argument of a root, and this can be any arbitrary root, right? Notice the index that is in here. This can be any root index. I can just find the limit of that function and then take that nth root of that limit instead. It's the same idea as this power law. Does that make sense? It's really the same idea as the power law. Because roots are just fractional powers, right? We also have these two special limits. The limit of a constant as x approaches a is just that constant, right? Because the constant function attains the same value everywhere on its graph. And the limit of x as x approaches a is just equal to a. Do these final two, 8 and 9, make sense? Asymptote? What about asymptotes?
Before it said, oh, I don't even know if you can hear me. Before it said when x equals a is the asymptote.
Under a different context. The context of that one was it here? No, it was here. The vertical line x equals a. So this is saying that, where were we? This is saying that the x values of the graph of yx, as the x values of the graph of the line y equals x get close to a, the y values of that graph also get close to a.
Is that the same for c, or was c just a constant or something?
C is just a constant here. So this is just saying that the limit, any arbitrary limit of a constant is just that constant. Because constants have the same value no matter what, right? Constants, if we were to graph them, they are horizontal lines. Awesome. We have a few other special limit laws. Really, all of the limit laws after the first few are derived from these first few. For instance, the root law and the power law. Well, the power law is derived from the product law, right? Because powers or exponents are repeated multiplication. And the root law is then derived from the power law. The limit of x to the n power as x approaches a is just a to the n, where n is a positive integer. This is a result of the power law and number 9 here. And we can also combine the root law and number 9 to get this one. Oh yeah, and the root law has the stipulation, if n is even, if it's an even root, we assume that a is greater than 0, because even roots cannot have negative numbers as their arguments. All right. Does this make sense? Is this okay? Yes, question.
Can you repeat what you said again about when the limit is x and it equals a? Because I was still writing and I forgot it literally as soon as you said it.
So like number 9 here, this is just saying that for the line y equals x, that as my x values get closer and closer to a, that my y values are also getting closer and closer to a. The idea of a limit is just as your x values get really, really close to some as your x values get really, really close to some number, that your y values are getting really, really close to some number in response, essentially. That's the idea of a limit. Does that make sense? Let's see. We could look at that example, but let me see how much left of 2.3 we have. In the interest of time, I don't know if I have enough time to do the example wherein it justifies every single step for a limit, for evaluating a limit. Although it's on page 97 of the textbook. It's a pretty good example, albeit maybe a little boring. Maybe it's a little bit boring of an example. It's also why I don't really want to. It's example number 2 on page 97. Or on the page that begins with this limit law. At least for me, this page begins with this limit law. I'm not sure on WebAssign what the page begins with, but it's directly after this limit law, after limit law 11. Let's look at evaluating limits using this method called direct substitution. If f is a polynomial or a rational function, and a is in the domain of f, then the limit of f of x as x approaches a is f of a. Oh, Ruth, was that a separate question, or did you just not lower your hand before? Okay. Again, if f is a polynomial or a rational function, and a is in the domain of f, then the limit of f of x as x approaches a is just f of a. Functions that have this property are called continuous at a. So functions that have this property are called continuous at a. We're going to discuss continuity more in depth in 2.5, which is our next class. However, not all limits can be evaluated using direct substitution. For instance, finding this limit. I can't use direct substitution here. Why not? Why can't I use direct substitution? What part of this direct substitution property is not satisfied? Or what part does this break here? Yeah, the denominator would equal 0 if I use direct substitution, right? This means that a is not in the domain of f, right? Now, I can work this to a place where I can use direct substitution, though, because I remember factoring. How does the numerator here factor? The numerator is a difference of squares, right? It factors x minus 1 times x plus 1. Notice how these x minus 1s cancel. At this step, I can apply direct substitution. You just like these? Oh, you better get used to it. This is calculus. I expect for you to know this. So if I use direct substitution here, this is just 1 plus 1, which is 2. You don't understand how the substitution works? At this point, because plugging in 1 won't cause any issues, I can substitute in 1 for x. So it's no longer x plus 1, it's 1 plus 1. Does that make sense? It's just once we work this to a place where, okay, once we work this, that's it. We evaluated the limit. It's not any deeper than that. Next one. Sure, but first we have to look at something else. First, we have to look at this fact. If f of x equals g of x when x is not a, then the limit of f of x as x approaches a is equal to the limit of g of x as x approaches a, provided that the limits exist. So if these two functions are the same when x is not a, then their limits are the same as x approaches a. That is a fact that is implicitly used here. The function x plus 1 is not exactly the same as the function x squared minus 1 over x minus 1, is it? Because the graph of this function has a hole at x equals 1. And the graph of x plus 1 does not. But these two functions are the same for every other x value. And because they are the same for every other x value, I'm allowed to say that their limits are the same whenever they approach an x value of 1, which is where this discontinuity is in the original function. This is just a fact that was implicitly used here. Does that make sense? Okay. How come whenever I think I'm making perfect sense, I'm not making perfect sense, and then whenever I think I'm sounding like a crazy person, everyone's like, oh yeah, makes perfect sense. I don't know what's up with that. Let's look at this. Ooh. We're starting to get into some interesting territory with some examples. Evaluate this limit. So the first thing I have to note here is that we cannot just plug zero. We can't just plug zero in right away, right? Because if I plug zero in right away, then we're dividing by zero. Can't divide by zero. What I can do is use some algebra. We're going to use some algebra and simplify this to something where we perhaps can just plug zero in. And I'm saying zero because we're looking at the limit as h approaches zero. So the first thing I need to do is go ahead and multiply this out. Right. We better be good. We better be getting pretty good at that by now. If I multiply it out, I get what? 9 plus 6h plus h squared. Then I have this minus 9. This is all over h. And I want to find the limit as h approaches 0 of this. And this is this. 9 minus 9 is 0. I'm left with 6h plus h squared over h. I still can't plug 0 in directly because I'd be dividing by 0. But what I can do is I can factor in h out of everything in my numerator. This allows me to carry out this division, which cancels the h here in the numerator and denominator. So this is the limit as h approaches 0 of 6 plus h. And now I can use direct substitution to plug 0 in for h. This limit is equal to 6. Easiest thing I've ever done. You notice that you substitute in the value that the variable is approaching. Does that make sense? You've been so confused? Yeah, we substitute in the value that the variable is approaching. How is h is not equal to 0 and letting h approach 0? What do you mean by that? Oh yeah, when allowing yeah. Yeah, but at the end here, we're allowed to use direct substitution because I have something that is a polynomial. It could be 0. It's just I don't always care about the function value here. But this is from our direct substitution property. That's not a direct substitution property. This is. If f is a polynomial or a rational function, and a is in the domain of f, then the limit of f of x as x approaches a is f of a. So I have a polynomial here, right? And a is in the domain of this, right? A is 0. 0 is in the domain of 6 plus h. So this limit is equal to the function value if I just plug that a in. Does that make sense? Oh boy, we still have a little bit left in this section. It's okay. What I'm going to do real quick, before I forget, I'm going to go ahead and I'm going to head over to WebAssign, and I'm going to postpone the 2.3 homework. Because we're not going to have quite enough time to finish it. I wouldn't woo too quickly because we still have a bunch of homework next week as well. So remember that we still have 4 homeworks next week. Or no, we don't. Next week's spring break. What the heck? You will see me next week because you will see me on Monday. We're still going to meet on Monday. Yeah. But yeah, spring break technically starts Tuesday. There will be homework next week. The homework will be the 2.3 homework, which I'm currently postponing, and the 2.5 homework. It's okay. Yeah, the 2.3 and the 2.5. The 2.5 homework is listed after the 2.7 homework for some reason for me, so I got tripped up. But it must be because I don't have it scheduled correctly right now. You will see me only Monday next week because next week is spring break from Tuesday to Thursday. You will see me only Monday. Let me go to my reschedule assignments thing real quick. Monday, we are going to finish discussing section 2.3. We are also going to discuss section 2.5 on continuity and sections 2.3 and 2.5 will be due next Saturday. Let me go ahead and I'm going to go ahead and postpone these dates here, the 20th. Two dot three, okay, and 2.5. There it is. Found it. And these other ones need to be postponed to a later date than that. Let me go ahead and save here. Save. The lab is still due Sunday, and there will still be a lab due next Sunday as well. Do we have all the tools that we need for the lab? Let me check. Let me double check to make sure that we have all the tools that we need. Oh yeah, we have all the tools we need because in my foresight, I did not put 2.3 on the lab. What are the labs? So there are lab assignments in this class every week. To access the lab assignments, go to Blackboard and click on coursework. Lab 1 is posted currently. You will click on it. It is a Word document. There are several questions there. You must answer them all. Labs will be due on Sunday every week. You can submit your lab assignment to me either by taking a picture of your work and your answers that you did on paper and sending that to me via email or via the upload space on Blackboard, or by like typing it up in a document and sending that to me also. Both of those are acceptable. Does that make sense? Also, please do me a favor and very clearly label your answer in some way. Like, please clearly box in your answer or something. Oh yeah, a scanned PDF is fine. Literally taking a picture with your smartphone, as long as, you know, you take a decent picture, is also fine. Make sure that the picture is not too far away, right? Make sure it's sufficiently close to your work that I can read it. You still have numbered attempts on each question. Let me check those settings. Oh wait, can I can I check these settings? Let's see, view. Oh wait, okay, I have to go into the class settings, I think. Sorry, I haven't used WebAssign in a few semesters, so it's a little bit. Assignment templates, no. I'm the instructor for this course. Why can I not edit? Let's see. Score view, edit class settings, class schedule, communication, class settings. Huh. You like my open math better? My edit button does not work. Interesting. My edit button does not work. Let me ask my colleagues about this. How many attempts do you have? Did you get cut off on a certain number of attempts? Some have 5, some have 3. Huh. All right. That's interesting. That's interesting. Well, I'll see if I can change that. That hasn't happened before. So I'll see if I can figure it out. I would like to give you unlimited attempts. My options, settings, my assignments, maybe. Where's my assignments? Maybe I click on assignments. My assignments. Oh no, those are assignments that I made. Okay. Oh no. Remember, on the syllabus, no extra credit, none. This could be a result of copying over my stuff from my previous calculus class for some reason. This may have affected this cheater, more like being efficient. I'll ask my colleagues about this. I'll send an email out and I'll see if I can figure this out. Because I do want for you to have unlimited attempts if I can give them to you. So I'll see if I can figure it out. Yeah. Oh, the pizza man's there? Nice. Yeah, have a great one, everyone. Please enjoy the rest of your night. Enjoy your weekend. And please, I know the temptation must be very real to not show up to class on Monday, but please do show up to class on Monday. Oh, I will. Unless you were saying to have a good night, in which case I also will. I was going to say I'm definitely showing up to class on Monday. Have a great one, everyone. Okay. Please enjoy yourselves.